Freddie, how's it going?
Going all right. How about yourself?
Yeah, it's going all right. It's going all right. Hey, Paco, how's it going? I think you're muted, but you nod your head yes.
Oh, I'm muted. Sorry. Keep forgetting.
A great game of our time. Oh, I'm muted. Yeah, we all play. We just don't realize that we're playing.
Mm.
It's a thinker. So we've had 2 job talks already this week. We have 3 more. They've been good.
So number theory one's on Thursday, if I remember correctly.
That is correct. Yeah.
Cool.
So today is someone who's studying manifolds, kind of on the border of topology and geometry. Tomorrow is number theory, and Friday is algebra. Someone is doing some kind of categorical something in algebra, representation stability, and other things. Yep. All right. Any questions about our course? Okay, so as usual, we have problem session on Friday. So please, I have not added any more problems to the list of problems. I think maybe there's like a thing or two that I could add from my lecture notes. So maybe at the end of this lecture, if I remember, I should go back and do it. And yes, I remember saying before, there are some exercises at the end of the chapter. So I think there are at least a couple worthwhile exercises in chapter 1. So I'll go back and add some. Yeah, it is occurring to me that in order to, in order to have class field theory be a significant component of the course, which is supposed to be, I think I'm going to have to be more selective in my coverage of the text than I've been so far. So, things that are proved nicely in the course text may or may not be proved in class. Okay. So if there are no further questions, we'll get back into it. All right. Right. So the topic of this lecture is, well, now for me, now we're really talking about finite groups kind of in earnest. Yeah, so again, I really didn't want to assume the group was finite. And there's something kind of really kind of unexpected, I think, that you can do if you have any finite group. And so the hint for this comes from probably the most interesting cohomology, co/homology computation we did. So before we did a finite cyclic group G, right? So this was just an application of, hey, here's a nice free resolution of Z as a ZG module when G is finite cyclic. And so what did we find? We found that for even n, as long as n is at least 2, the cohomology groups are the invariance modulo of the image of the norm, which was exactly the same as what the homology groups were when n is odd. Okay. On the other hand, when n is odd, when n is odd, the cohomology groups are the kernel of n. That doesn't make sense. I'm sure I mean the kernel of the norm map. I do mean the kernel of the norm map. Okay, so if the group is finite, then we have a norm map from the group into its invariance, where you just you make it invariant by summing over all the group elements. Okay. Right, and so you see this thing and you're like, okay, so there's some interesting stuff going on. On the one hand, there seems to be it's interesting that the homology and the cohomology are kind of the same as each other. There's like an odd even jump. So that's interesting. And then you see it's like almost like a periodicity here. It's almost like the homology and the cohomology groups alter. I mean, there's only two different things, so far that they could be. So it's like the group homology taken together with the group cohomology is like too periodic or something. So that's interesting, except that's ruined a little bit by what happens at n equals 0. So, okay, I'm a little late to the party that, we're looking at natural numbers. So an odd natural number must be strictly positive, but an even natural number could be 0. And so the even natural number is an exception to each one of these. Whereas in these other cases, yeah, so you see that, right, so for n equals 0 here, we're getting a different recipe. Here we didn't mod out by the image of the norm map, whereas for all larger even integers we did. And then here, if you compare this to what the group homology is for larger even integers, here we took the basically the co-kernel of the augmentation. That's maybe not the right way to say it. We modded out by the image of the augmentation ideal. Here we did that on all of them. Here we only did it on the kernel of the norm map. Okay, so what you see is that they're slightly different. So all the higher even cohomology groups are a quotient of the H0, and all the higher homology groups are a subgroup of the H0. Okay. And so, all right, right. So it's almost the case that group homology of a finite subgroup is too periodic, but you see that the zeros are screwing it up. Well, okay, how about we make this definition? At the moment, we've only, this is only for a finite cyclic group. So it's like, why do we think this is going to do anything? I'm just trying, it's better motivation than you find in the textbook, I guess. So let's go with it. So how about we repair maybe this is like vaguely now, like it's been a really long time. I just realized this kind of reminds me of like reduced homology groups or something, right? That's the thing. Anyway, so it's maybe it's vaguely analogous to that, but anyway, so we do H0 hat to be exactly the same thing that the higher even H's were in the case of a cyclic group. So namely, it's not just the invariance, it's the invariance modded out by the image of the norm map. That makes sense for any, again, it's easy to see that once you symmetrize by summing over the action of the group, you certainly get a G invariant. So no problem that the norm map is inside of here. And then here we get the kernel of the norm map modulo the image of the augmentation ideal. I mean, we define, yeah, and so again, this should be checked. So it's no problem. Yeah, by the way, the fact that the norm map is contained, image of the norm map is contained inside the G invariance, this is actually a special case of co-restriction. If we co-restrict from the trivial group and take n equals 0, so we get co-restriction from this is a map from the H invariance, which is M itself, into the G invariance. Okay, but what was that map? When n equals, that's the only case where I explicitly defined the co-restriction, and the co-restriction when n equals 0 is the norm map. Okay, so the fact that the norm map is contained inside of here is we've definitely seen that before. Anyway, it's easy. And then I also claim that the image of the augmentation ideal times M is contained inside the kernel. That's also the kernel of the norm map. This is essentially coming down to this profound statement that if you take any fixed group element, then the augmentation ideal is generated even as a Z module inside the group ring by group element -1. And so what happens if you take, and then for the norm map, we're summing over the elements of G. So if I sum over all the elements of G and I apply that to G -1, well, summing over all the elements of G and then multiplying is just going to permute these elements. And of course, I'm going to get the sum over all the elements of G. And then this is also going to be this. Anyway, this expression is clearly 0. And so therefore, this is what's underlying the fact that anytime you hit your element with something in the augmentation ideal and then take the norm, you are certainly going to get 0. Okay, so we can have these kind of reduced H0s. So what? Well, now something really kind of amazing happens. It's not super hard to prove, although I'm going to skip the proof of it. It really does seem to be due to John Tate, the number theorist. So what Tate observed is that for any finite group, not just a finite cyclic group, and any G module, you can, if you modify the H0, the H super 0 and the H sub 0 in the way that we just did, you can actually stitch together the homology and the cohomology into a really infinite sequence, into a bunch of Tate cohomology groups. So H hat n, those will be called the Tate cohomology groups of a finite group with coefficients in any G module. And the Tate cohomology groups will not just be parameterized by the non-negative integers, they'll be parameterized by all of the integers. So this is, I don't see any clear precedent for this in topology. It's kind of surprising that you can splice together cohomology and homology. Okay, so just by definition, when n is a positive integer, the Tate cohomology group is nothing else than the corresponding cohomology group. When n is 0, it's the modified H super 0, as we just described. Now, H negative 1 is the modified H sub 0. Okay, they can't both be H0, so there's like a little bit of a reindexing here. Okay, and so that is again, that's a submodule of the coinvariance. And then just with the most natural possible reindexing, if n is less than or equal to -2, then the negative indexed Tate cohomology actually comes out to be a corresponding group homology. Okay, and so I mean, you can plug in these things as well as I can probably, but you see that, for instance, the -2nd Tate cohomology is the first homology, the -3rd Tate cohomology is the second homology, etc. Okay, so all right, that's why, what happens. And so here's the main theorem which really justifies this. If you have an exact sequence of G modules, well, we could take group homology, and that would give us what we call it a long exact sequence, but it starts at 0 and extends a priori infinitely far to the left, but it ends, infinitely far to the left, but it ends at 0. Whereas or we could take group cohomology, that would start at 0 and extend infinitely far, probably to the right. This is, I mean, you've never seen such a long exact sequence. I mean, maybe you have. This is an actual, doubly infinite long exact sequence. Okay, and so it is kind of a a long exact sequence in homology is stitched together with a long exact sequence in cohomology. So that's exciting. Okay, that's good. And yeah, so this is a good example of the type of thing. Like I don't have anything better to tell you about. I have no secret insight into this. The proof in Harari is fine. It really is. It's not one of these results that pulls out some kind of black magic from homological algebra. There's no faceable functors or anything like that. It really is just a diagram chase using the snake lemma. So check it out. Okay, so instead I want to prove. I think maybe it's like in Harari it's like one result, 2 parts, and that was the first part, but the second part is different. So this is kind of interesting too. So remember, we haven't talked about it for a little while, but we talked about weakly projective, often called relatively projective modules. So these are modules that are direct summands of induced modules, and then the point being that by Shapiro's lemma, an induced module, and therefore also its direct summand, will be acyclic for group homology, the higher homology groups of anything but 0, the homology of a weakly projective module will be 0. And then dually, or whatever, we have weakly injective. This is a direct sum end of a co-induced module, and therefore by the cohomological Shapiro's lemma, all the cohomology groups of a weakly injective module, except for the 0th one, will be equal to 0. Well, now though, if the group is finite, we just proved last time that induced and co-induced are the same. So there was a natural isomorphism from the induction to the co-induction. Okay, and so therefore weakly project. I mean, if being a direct sum end of, I mean, if these two things are the same, then being a direct sum end of the same thing is the same condition. And so that's nice. So weakly projective is actually the same as weakly injective. Okay, and so therefore this one class of modules was acyclic for group homology and group cohomology at the same time. That's nice. That's most of, I mean, that's like, you know, infinity minus 2 of the statement of the theorem here. But now the claim is that actually even at the 0 level, because we modified the Tate cohomology, it was kind of reduced in the sense that I just said. We passed to a quotient on the cohomological H0 and passed to a submodule on the homological H0. That it, in fact, even the Tate H0 and the Tate H minus 1 of this class of modules will be 0 as well. So, you know, you've never seen something so acyclic. It's everything. All of the Tate cohomology groups are 0. Okay. This I will prove. I think, you know, it's a little more, maybe a little bit more interesting. Less of a diagram chase. Okay. No diagram chase. All right. So again, for n at least 2, again, this is the Tate. Again, you've just seen the definition, so it is just the usual cohomology. And again, oh yeah. So one thing I guess I didn't read this here. So again, being weakly injective equals weakly projective means being a direct sum end of induced, which means is the same as co-induced. So as usual, not even for the first time, everything in sight is an additive functor. So it's certainly going to take finite direct sums to finite direct sums. And you stare at that for a little bit and you say, okay, I really just, I will immediately reduce to the case where my module is actually, if I can prove that this guy is equal to 0, then obviously both of the direct sum ends are also equal to 0. So that's fine. So yeah, so we sort of can reduce to the case where we have a module which is, well, co-induced when we want it to be co-induced and induced when we want it to be induced, because it's the same thing. Okay, so for n greater than or equal to 2, I want to say that it's co-induced because, again, we proved by, this was exactly the special case h equals 0 of the cohomological Shapiro lemma, that vanishing. Similarly, if n is less than or equal to -2, then this is the homological Shapiro lemma because the thing is induced. It's the same. All right, so we just have to do n equals 0 and n equals -1. Okay, so in particular, what are we showing? So now we're computing the invariance of an induced module. We're saying the invariance of an induced module are no more than the obvious invariance, which is the image of the norm map. And if you think about this, this kind of sounds familiar. So this is a generalization of something that Tyler did, and maybe someone else did it before Tyler, but Tyler did it most recently. And so yeah, so let's just see that this is a mild generalization of this part of this exercise. So again, one thing is, you know, do we want to use that it's induced or do we want to use that it's co-induced? You might have guessed co-induced because we're doing something with cohomology, but no, it's better to use that it's induced. And so therefore it's just by definition, it's of the form some Z module tensored to the group ring ZG. Okay, with the, you know, just the group acting on the left. And so by the way, if X is equal to Z, well, yeah, then we're reduced to the claim that the G invariants of the group ring are or the image of the norm map, which is exactly what Tyler proves. And it wasn't so hard, right? And so the general case is really similar. Just, I don't know, I like this notation. So in fact, if you think about it, what sort of object are you getting when you tensor an arbitrary commutative group with ZG as a ZG module? I decided I wanted to call it XG. Kind of looks good, right? ZG tensor Z with X should be XG. This is not a ring anymore. It's a G module, okay? But what should XG be? Well, it's a direct sum of copies of X indexed by the elements of G. That sounds pretty good, right? And how does G act? In the obvious way, it acts just by permuting the factors, okay? Just like the way G acts on the group ring. And so the same as before, what does it mean to be to be an invariant here? Well, for every G in G, you're getting an element, X sub G or something. And G is acting just, literally just by permuting these factors. And so if G is supposed to be invariant, then, well, all the XG coefficients have to be the same, right? The action is obviously, obviously the G action is transitive. And so the invariants are just kind of the diagonal elements, the ones where the coefficient is the same every single time. And that is the image of the norm map. Okay, so the ones, if every diagonal coefficient XG is equal to each other, then we took the norm map and we applied it to X. Okay, so right. Anyway, so what I'm saying is that this is such a mild generalization of this invariant calculation that we already did that you do it in exactly the same way. Okay. Now for n equals -1, well, now we want to show, it turns out, let's use that it's co-induced and show that the kernel is equal to, the kernel of the norm map is equal to the image of the augmentation ideal. Again, what we already knew, what was easy was that the image of the augmentation map was killed by the norm. So we have to show that there's nothing else in the kernel of the norm map. Okay, so I guess this takes more words. So again, what does co-induced mean? Oops. Just Z-hom. Okay. Yeah. So Z-hom from ZG into our commutative group X. And again, well, that's a free, this is certainly a free Z module with basis G, so that you can identify just with the collection of all maps from G into X, with pointwise addition and a G action that I'll remind you of in a second. And so again, is this a familiar thing? Yeah, if X is equal to Z, then we're looking at the maps from our, now I'm about to use that G as finite. So the maps from our finite group G into Z, well, that's Z to the G. That's what the maps from any set to any other set is. And that's the group ring, right? So the group ring is a direct sum of a bunch of copies of Z indexed by G. What's the G action? The G action is on the right this time, if you just remember what the G action is on an induced module. So it's, as a function, you act on the argument by right multiplication. So okay, so in this case we get ZG, where the G action is the right action instead of the left action. That doesn't bother us, right? And so what's the norm? The norm is, so what is the, if F is a map from G into well, Z at first, then what is the norm? Well, the norm is sum over all the elements of the group acting inside on the right. And you look at this and you're like, yeah, that's basically the augmentation map. Again, this is a map. I mean, this is a map, but it's constant. You see that we're summing for every element of the group, I'm summing over all of the values. Okay, so this is kind of the, yeah. So for this is the map that to every group element it assigns the augmentation homomorphism. Okay, so this map is essentially the augmentation map, and so right, and so therefore its kernel is the augmentation ideal by definition, which is the augmentation ideal applied to A in the case that A is equal to Z. And then again, the general case is no more difficult really. So now we're doing maps from G to X, which is X to the G. That's great. I get to use that XG thing that I just defined again. Now the G action is on the right. And so what are we saying here? We take an arbitrary element of XG, which looks like this, right? So a formal G linear combination of elements, sort of free G linear combination of elements of X. And so what are we really saying here? Again, the kernel of the norm map is where you're adding up all the coefficients. That's the norm map. So the kernel of the norm map is the collection of tuples here that just for which the sum of all the components is equal to 0. And so what are we saying? We're saying if you have a finite sum like this, such that the sum of the coefficients is equal to 0 in X, then if that happens, then X lies in the subgroup generated by these guys, right? Because the augmentation ideal is generated by group element -1 applied to things. Okay. So what am I saying? I'm saying that the sum of the components is equal to 0 if and only if it lies in the subgroup generated by these guys. And I don't know, you may not, I'm going quickly, you may not recognize this, but this is just not hard at all to check. So I'll give you an analogous linear algebra statement that is like one level less scary and should convince you that this is easy. So what if we were in Rn instead of the direct sum of G copies of X, and I was just looking at the hyperplane where the sum of the coordinates was equal to 0, okay, an excellent hyperplane, right? And so my claim is that subspace is generated by differences of standard basis elements, which itself is generated by any standard basis element minus the first standard basis element. So of course this hyperplane is generated by these basis elements. It's a trivial linear algebra computation. Okay, so yeah, you just once you realize that there's just nothing deep going on here, and then yeah, you just check. I mean, using this, it is no problem to take an element whose sum of the coordinates is equal to 0 and explicitly write it as a sum of G minus 1 times something else. No problem. Okay, so that's my discussion of the fact that weakly projective equals weakly projective modules are like completely acyclic for Tate cohomology. So all of the Tate cohomology groups vanish on weakly injective equals weakly projective G modules, including 0 and -1. Okay, so really quickly, the Tate cohomology can also be computed using standard cochains in a certain sense. There's something called a complete standard resolution of Z. It doesn't really make sense in cohomological algebra, in homological/cohomological algebra general terms, but what it means is this: I have a doubly infinite sequence. I have a Z-indexed exact sequence of ZG modules, okay, free ZG modules, and there is some general recipe, but you can go back and look. Each one is one of these things, so a group ring of a certain number of copies of G, which by the way is very similar to what our standard resolution was before, although we didn't say it in exactly this way. So what I'm saying is that there is a specific, very long exact sequence of free ZG modules. Why am I saying it's not really right to call it a resolution of Z? Well, where's the Z, right? It's infinite in both directions, so it doesn't get a chance to like end at Z or start at Z because it's infinite in both directions. But anyway, but it's still it's a what you call it? You still have this resolution, and then yeah, and so then you have these. Oh right, what are the maps, right? So the maps are they really do look exactly the same as the yeah. So these are whatever I don't know whether they're boundaries or co-boundaries, but these are the Ds, very similar to what they were in the first case. And so again, you have to check by hand that this is exact. And then it turns out that in a fairly straightforward way, using this complete resolution, you actually can compute the Tate cohomology. All right. Yeah. Okay. Okay. So that's what I wanted to say about that. Yeah. I mean, again, you can sort of see what's happening at 0 and -1. For the higher ones, it's the cohomology that we already talked about. You can see that we sort of skipped over our discussion of the standard chain complex for group homology. What do you do? And you take that same standard resolution of Z over ZG that we did before, but then you do the, homologically, algebraically appropriate recipe. So instead of, what did we do? Instead of like Hamming with Z and taking the cohomology of that, we should tensor with Z and then take the homology of that. And then there's some, touching up exercise to present that in terms of, reasonable looking, chains and boundaries. But okay, so you can do that. And if we have the need of, expressing group homology in terms of chains and boundaries, then we can do it. Okay. I mean, this is doing it all at once in a certain way. Okay, so the next thing I want to do is I want to talk about restriction and co-restriction. I mean, I don't really want to talk, I mean, I kind of do want to talk about them. I don't have time to say that much. They exist in Tate cohomology. So again, restriction to any subgroup of any group makes sense. And co-restriction for any finite index subgroup makes sense. And so if G is finite, well, sure, great. You can do both of these maps for any subgroup. And so what's going on? We have an N sub G, which is the norm. M is a G module here. So we have the norm map for G modules. M is also an H module, of course. So we have the norm map for H modules. And no problem to see that the image of the norm map of the G norm is a submodule of the H norm. And I guess this is writing that out a little bit. So if you just say, if you're summing over G, then it's like summing over H and then summing over cosets, basically. So I'll let you think about that. Again, there's a little bit of a, do you want to do like left cosets or right cosets? I think you want to do right cosets, but anyway, you can, this might be, maybe this might be a good exercise actually. Just, something very concrete, work it out. Right. So what are we saying? We're saying that the restriction also makes sense on the modified H0. Okay. So, yeah. So the restriction MG, the G invariants are always contained in the H invariants. It's a stronger statement to say that it's invariant under the group than it's invariant under the subgroup. And because of this fact, it makes sense to mod out by the norm maps on both sides. Okay, so this is the sort of the Tate 0 restriction, and then yeah. So for instance, by cohomological nonsense, you can define the higher restriction maps. Okay. Yeah. So again, you could do this by dimension shifting or some such. This is a little bit out of order. I realize this was a corollary to the thing that I just proved. So dimension shifting works even better on Tate cohomology. We haven't done like a great application of dimension shifting yet. Maybe that should be a good. I should have that be an exercise. But the dimension shifting doesn't work quite as well at n equals 0 in general. But Tate cohomology, that difficulty has been fixed. And so here, if you have an exact sequence of G modules where the one in the middle is induced, which is the same as co-induced, or actually even weakly projective, which is the same as weakly injective, well, then it's totally acyclic for Tate cohomology. And so therefore, when you have a long exact sequence, well, you know, if something in the middle is totally acyclic for the homology, then you're just going to get isomorphisms between the other two guys. Okay? But note, so that's telling you that the nth Tate cohomology group of B is naturally isomorphic to the n plus first Tate cohomology group of A. And what does that mean? I mean, that allows you to, in particular, every Tate cohomology group of a module. Again, also you can embed any module into a co-induced module. We did that. We did that as well, canonically even. Or you can surject. You can also surject it onto an induced module, so you can have it either way. So what is the consequence of this? The consequence of this is that every single Tate cohomology group of any G module is, you know, you can change the index. You can compute for any n. You can compute h hat n of your G module as h hat of whatever you want the index to be, 0, whatever you want of some other module. Okay, so there's just a total, you know, in terms of what these groups come out to be, there's a total symmetry in the indices. Okay, so you can, you know, you can shift all the indices so that you're only ever really looking at an H0 if you want, which is potentially useful because, you know, some of the things we're defining explicitly for H0. Okay, there's also a co-restriction. Okay, so let's see. So here, I guess the question is, how are we defining? I didn't talk about it. So there's a co-restriction in group homology as well. When you have a finite index subgroup. So here I'm just telling you, same as before, I should tell you what I should at least tell you what it is on H0. And so yeah, this is what it is. So these are the co-invariants with respect to H, right? And these are the co-invariants with respect to G. And so yeah, the augmentation ideal of H is contained inside the augmentation ideal of G as a subgroup. And so yeah, so here this is just the, you know, this is the usual surjection that you get by modding out by something smaller to modding out by something bigger. Okay, so this is just the, you know, just the evident surjection map. And so again, by homological nonsense in terms of faceability and delta functors and stuff, read about that if you like. This uniquely extends to a co-restriction morphism of homological delta functors. So what does that mean? It means that there's a unique way to extend this 0-level co-restriction to a co-restriction on all the homology groups, so that you get something which is compatible with exact sequences, okay, in a certain sense that I'll leave you to look up. Okay. Right. Let's see. Okay, and yeah, here's another exercise. Also here's a restriction in H0. So ordinary H0 here. And so what is this? This is Harari's notation, norm prime of G over H. So this is a map that goes from the coinvariance of G to the coinvariance of H, and that's not as obvious a map. What are you doing? You're summing over a system of coset representatives. You can either sum over the left coset representatives and put an inverse on it, or you can sum over the right coset representatives. And yeah, so again, this looks like an exercise. What's the exercise? I guess the exercise is to show that first of all, you do get two well-defined just homomorphisms of a billion groups this way, and that they're equal. Okay. So again, I'm taking this kind of quickly, but you can definitely define restriction and co-restriction on the group homology, group cohomology, stitch it together to get the Tate stuff, right? So here's the thing. So I just defined co-restriction on the unmodified H0, right? But I also want to define it on the modified H0, which is not the entire covariance, it's the kernel of the norm map modulo of the augmentation ideal. So the next exercise is to show that you have sort of the right thing in order for this, in order to be able to, restrict the co-restriction map. Okay, so that it turns out that this map up here, this, yeah, maybe it would be, maybe it'd be more helpful to call this the norm prime of G over H. This does take the kernel of, oh wait, no, I'm getting confused. Sorry. That was the restriction, so I shouldn't have done that. Sorry. Yeah. So this is the co-restriction on homology, which was this map. Okay, just the quotient map. Yeah. So the exercise. Sorry. I'll write this up. Of course, the exercise is to show that just under this quotient map, if you look at the kernel of the norm map under G, it will be just as a subgroup of M is contained into the kernel of the norm map over G. Okay, that sounds quite easy now that I sound it out. But okay, you can still show it. And so what does that mean? It means that just defining it kind of at the smallest value, the H hat sub 0, which is H hat super minus 1, you do. So I am quickly, but I am very directly telling you what this co-restriction is, sort of for the smallest homology piece of the Tate, the Tate cohomology. So this is what it is on H1. It's this. You take this quotient map and you restrict it to the kernel of the norms. Okay. All right, so that was quick, but you should take from this that there are restriction and co-restriction maps in Tate cohomology. And yeah, so here's the, I should slow down. This is my last page for today. All right, whatever. So here's a nice result. Yeah, so application of all this. You have a finite group, you have a subgroup, therefore certainly a finite index. Let's call the index M. You have a positive integer n, totally arbitrary. You have a G module capital M. So the first thing is that if you restrict and then co-restrict, then that gives you multiplication by M. And so again, this is probably a good exercise too. So you prove this at level 0, or what, you know, the smallest value, whatever that is. And for instance, just on regular group cohomology. So what are we saying? We're saying that if you have a G module, what do you do? And you just view it as an H module, and then you hit it with the norm map. Yeah, let me go back actually just to see how we. Right. There we go. Yeah. So there's some general nonsense, but we're starting with this very simple case. What is the co-restriction map here? It is a kind of relative norm map. It's summing over a set of COSA representatives for G mod H. Okay. Right. And right. So what am I saying here? So I'm saying, in fact, that you should have been. I guess I just didn't say this last time. Did I? I didn't. But you can just check directly that for this map, if you restrict and then you co-restrict, then you're going to get multiplication by n. In fact, that's quite multiplication by the index. In fact, that's really trivial. I'll just do it right now. Well, we're starting with the G invariance. So then we're injecting the G invariance into the H invariance, but we still have the G invariance. And now I'm doing this process but I'm inside the G invariance, right? So acting by G is not very exciting because I'm inside the G invariance. And so therefore each single one of these acts by 1. And therefore, well, what is this map? Well, gosh, how many elements do I have? I have the index of G and H. So yeah, this map definitely is multiplication by the index of H and G on the G invariance. Okay, so you see, I should, that's so simple, but I think correct me if I'm wrong, I don't think I said that before. So that's where this profound identity is beginning its life. At n equals 0, it's completely obvious that restriction composed with co-restriction is multiplication by n. Did anyone want to ask me what the composition the other way is? It's nothing good. If you think about it, like it just sort of can't be. And if you do it the other, again, this is like a norm map. So it's like you took a norm map and then you like restricted it. So yeah, so let me think for a second as an example. Think for a second. Thinking. Yeah, so one instance of this would be like if I had a finite Galois extension of fields, as we'll do later, and then the invariants are literally the Galois invariant. So if you have L over K is a finite degree of Galois extension, then the G invariants are just K. Maybe I'll take H to be the the trivial group there. And so yeah, so here what's going on? So here, if I restrict, then the restriction map, I should be writing something down. I guess I just don't feel like it. I'm sorry, maybe I should. I should. So the example that I want to do here, so example, let's have L over K, finite Galois. Let G be the Galois group. Hey, we're doing Galois cohomology. Right, and so what am I doing? Yeah, so I'm going to take M just to be L, additive group. Evidently, this is a G module, and they call it Galois theory, the G invariants are K, and let's just take H to be the trivial group, right? And then we can see what's happening here. So what is the restriction map here on the n, I'm only doing n equals 0. So the n equals 0 restriction map should be going from mg into mh. Well, h is trivial, so mh is m. Okay, so what is this map? What is this map?
Just the embedding K
Yeah,
to
so this
L.
is just K getting embedded inside L. Great. And then we have a co-restriction, which goes in the other way from MH into MG. And what is this map? So this is a map that goes, well, the other way. So it goes from L to K. And what is this amazing homomorphism that goes from L to K?
The norm?
No.
Trace?
Trace, yeah.
Trace, sorry.
Switch to the multiplicative group, and then it would be the norm. Yeah, so the norm is not a additive homomorphism, so I tricked you. Yeah, so this is the trace. It manifestly is the trace. There's no the sum over the Galois conjugates. That's the trace. And so yeah, let's just check. So what I just said was I get something. Yeah, so let's do n as the cardinality of G, and so let's check. I said that something nice happened if we restricted and then we co-restricted, right? So so I have K into L followed by the trace. Okay, so now I'm taking the trace from L down to K of something that is actually already in K. Okay, and sure, that's going to be n times x, right? Among other things, it's like the trace of the scalar matrix multiplication by x. But what if I did it the other way? So now I'm taking the trace right? And you look at this and you're like, well, it's the trace regarded as an element of L. So this is still the, is really still the trace. I mean, it's definitely not multiplication by n. You see what I'm saying? So just there's not a it's not a crazy thing, but it does not just come out to be multiplication by some integer or something. It just, yeah, it's something. It doesn't. It's not as simple a map as we got in the other direction. Okay, but you should have asked. Should always ask. All right. Well, that for a second I was afraid I was going to finish my lecture early, which is like the worst of all possible sins. So I'm not worried about that anymore. So sorry about that. Okay. Yeah, so again, if you restrict and then you co-restrict, you get multiplication by the index. Spoiler alert, I'm not going to tell you anything similar general nonsense as for the regular cohomology. So again, I will make an exercise. I think it is a good exercise to understand what kind of general nonsense you use. I just proved that on regular H0, restriction followed by co-restriction is indeed multiplication by the index. And so then by general nonsense, including some dimension shifting, if I remember correctly, is what you want to do to establish that for the on cohomology. And so that's a good exercise. And maybe once you do that exercise, you're like, yeah, maybe Tate cohomology works similarly. This has a really nice consequence, which is that this Tate cohomology group, which again is a Z module, right, is an M torsion Z module. Okay. Why is that? Well, I can definitely prove that. If you just take H to be the trivial group, right, if you co-restrict to the trivial group, then Tate cohomology of the trivial group is always trivial. Okay. You do want to examine n equals 0 and n equals -1 to check that that's true, right? Because even for the trivial group, like capital H0 would be the invariance, and the invariance of M under the trivial group is M, which is very probably not equal to 0. But the modified Tate cohomology is the invariance modulo the image of the norm map. If the group is trivial, both of those things are M, and they cancel out, and you get 0. Okay. Similarly for the H hat sub 0, which is H hat super -1. Okay. So indeed, for Tate cohomology, if you restrict to the trivial group, then you get 0 all along. And then if I co-restrict, I got multiplication by M. So if I restricted and got 0 and then did something else, then I certainly got 0. So therefore, multiplication by M acts as 0, which is what I was trying to prove. Okay, that's very useful. And then the last one is kind of nice too. So if M is finitely generated as a Z module, then all of the Tate cohomology groups, all of them again, are finite. Not finitely generated, not finite type, finite. Okay, why is this? Any thoughts? Should be like a two-step process. What's the first step?
That it's finally generated, and then use the fact that it's M torsion to make it finite?
Yeah, you're a little quiet for me anyway, but I heard you. Yeah, so that's right. So we just saw that your torsion, right? That was literally the last thing that we said. And so of course, if I'm telling you, if I have a commutative group is finite if and only if, profound fact, it's torsion and finitely generated, right? So that's kind of a general criterion for finiteness of a commutative group. We just proved that it was a torsion commutative group, so we have to prove that it's finitely generated. And so now the fact that M is finitely generated should be telling us that these guys are finitely generated. Why is that? Yeah, so you see, I just said it's torsion, so it's enough to show that it's finitely generated, but I claim that already the finite generation occurs on the cochain level. So what do I mean? I mean that, if you want, this really is the, the cohomology of some complex. And I'm claiming that if M is finitely generated, then even the terms in the complex before I take kernel not image are finitely generated Z modules. And so again, submodules and quotient modules of finitely generated Z modules are also finitely generated. So that would be great. Okay, and so then maybe I'll let you think about this. I did give you quickly, I did give you a general recipe somewhere. Here, yeah. So I did quickly wave my hand at this general recipe for computing Tate cohomology on the cochain level. And you kind of, so you have to convince yourselves that that these guys are already finitely generated if A is finitely generated. Okay. Stop and think about that for a second myself. Yep. Okay. Yeah. So that's why that's true. Okay. So yeah. So this is nice. So if you do Tate cohomology of a finite group and a finitely generated module, then you will get actual finite groups in general. This is probably, I mean, well, I'm still technically over time, so I feel okay. This is probably a good place to stop. Well, no, maybe I'll say just a little bit more. There's again, I'm throwing a lot of kind of general, a lot of maps are being defined. And so there's actually quite an interesting special case of this. You take your finite group G, you take its obviously finite subgroup H, any subgroup you want. I just defined a big old restriction and a big old co-restriction on Tate cohomology. So it turns out you already get a very interesting map if you take your module to be Z, which standard convention means trivial action, and you take the -2nd group cohomology, which remember is the first group homology. And now we see that we didn't waste as much time as we thought, because at this point Harari explains why the first group homology with coefficients in G is the abelianization of the group, which is also isomorphic to augmentation ideal modulo its square. We did that before. So and again, this is if you're thinking about Eilenberg-MacLane spaces, it would have to be that, but it wasn't at all hard to do. And so yeah, so what is this map doing? It's giving us a map from, so again, this thing resolves to the abelianization of G. This guy resolves to the abelianization of H. And so what are we saying? We're saying if you take any finite group G and you take any subgroup H, then there's some canonically defined homomorphism from the abelianization of G to the abelianization of H. You might get confused and be like, that's not interesting. What's not interesting is that there's a homomorphism in the other direction, right? Abelianization is a functor, right? So I mean, abelianization, of course, is mod out by the commutator subgroup, right? So if I have any homomorphism of groups, I do get a homomorphism from the abelianization to the abelianization, right? But that goes in the other direction, right? So the kind of obvious homomorphism would be from the abelianization of H to the abelianization of G, because the map is embedding H inside of G. We're saying, no, you have a homomorphism in the other direction. That's interesting. Okay, and so I think this is what I just said. So yeah, you take out all the cohomology, and for any subgroup of a finite group, there's a certain canonical homomorphism from the abelianization. And again, you switch it around and you're like, yeah, of course there is, but this is not trivial at all. This already is a pre-existing thing in finite group theory. It has a name. In English, you call it the transfer, okay? And in German, you call it the Verlagerung. And because of this, you often denote it by V. And because of this, American mathematicians in this area confuse the words Verlagerung and Verschiebung, because these are two German words that begin with V, and the corresponding things are denoted by V. And so the Verschiebung is like some kind of like Cartier dual of the Frobenius map or something, something like that. So it comes up in the theory of like group schemes in positive characteristic. Okay, so this is a map. Again, I think now it's like, okay, but seriously, now I'm really paying attention. How do I define this map, right? The way that we define the map was like, should we do it by dimension shifting? Should we do it, via these Tate cochains, or whatever, which, we gave we would really like to have a hands-on description of this map, and so we'll do that. Harari has a very nice discussion of this, so I'm not saying I'll do all of it, but I'll give you the high points. So yeah, so in the next lecture, we will address Harari's explicit, it wasn't due to him, but there's a very, very down-to-earth explicit description of this transfer map. Again, I don't think group theorists defined it as the restriction map in -2 Tate cohomology. I think they had some group theoretic way of looking at it. And then in particular, there's a special case this is that he proves is really a non-trivial theorem in group theory due to Furtwängler. And so if H is the derived subgroup, the commutator subgroup of G, the thing that you mod out by to get the abelianization, then you get a transfer map from the abelianization of G to the abelianization of the commutator subgroup. And it turns out that that map is always trivial. And it's not obvious at all. I think the proof takes like a couple pages. And I confess I don't remember exactly why, but this should actually come up in our later discussion of classical theory. Okay, that's it. Any questions?
Can you go back to part B of the theorem at the top of the page you said? Is that M supposed to be the size of the group, not like the index?
No, it should be the size of it should be the index. Here?
Yeah, that part B.
Oh, it should definitely be the index. Why? Yeah, again, I gave you the proof, right? So you restrict, this is, the co-restriction is, this is the restriction from G down to H, and this is the co-restriction from H up to G. And so, yeah, it should definitely be,
But in the proof, you took H equals trivial group. Not the trivial subgroup.
Oh, maybe I'm confused. Let me think for a second. I think I am confused. So I see your point. Let me think for a second. Yeah, so if I see what you're, of part B.
Yeah, just part B.
Yeah, you're right. You're exactly. I think part A is stated exactly right, and you are exactly right. So this should be, yeah. Yes. For exactly what you said, because H is well, I said it was the index of H, but I didn't say what H is. And then I took H to be the trivial group. So I'm not wrong, right? So much as I could have said it better. Yeah, it's the index of the trivial group inside of G, which is how we proved it. And you are correct. That could be more directly described as the order of G. Okay. Any other questions? Okay, well, back on Friday for a problem session, and then next week we're going to learn more about the transfer, which is nice. Yeah, no, it really does come up. Okay, well, see ya.
See ya.